Have you ever wondered how a team of robot detectives manages to solve a mystery without speaking a single word? Or how a tiny smart thermometer in a garden knows exactly how to whisper its temperature to the internet? Behind these everyday interactions is a hidden layer of organization. The artificial intelligence brains and smart cities we rely on use specific blueprints, called messaging architectures, to communicate. By setting up organized, predictable ways to share information, these systems prevent digital chaos. This ensures that thousands of complex pieces can work together smoothly. Let's step into our toy detective agency to see one of these blueprints in action. In the world of artificial intelligence, this approach is known as the Blackboard Pattern. Think of our robot detectives as what engineers call autonomous entities. They are independent thinkers, each working on their own specific part of a case. In the middle of their office is a large chalkboard. This board acts as a common knowledge base, a single, central place where all the clues are kept for everyone to see. When a robot uncovers new evidence, it doesn't shout across the room. Instead, it quietly walks up and adds a clue to the blackboard. The other robots are constantly watching this board. When they spot a new shape or pattern that matches their own specialized knowledge, they step up and add their own data to the growing picture. By layering these small, specialized observations on top of each other, the robots can piece together a complete solution, even if no single detective knows the whole story. Now, let's head over to the local radio station to look at a completely different blueprint, the publish and subscribe architectural pattern, often just called pub-sub. In this setup, we have a publisher. Think of the publisher like the town DJ, spinning records and broadcasting music out into the airwaves. The DJ broadcasts that music on a specific radio frequency. In messaging architectures, that exact frequency is called a topic. Across town, anyone who wants to listen simply tunes their radio to that specific topic. In software, we call these listeners subscribers. They capture the exact information they are interested in. This design works because the communication is asynchronous. The publisher doesn't need to know the names, locations, or even the existence of the subscribers. The DJ just plays the music, and the kids just listen when they are ready. This creates a system that scales incredibly well. Whether there is one subscriber listening or 1 million, the publisher's job stays exactly the same, making it perfect for networks where the audience size constantly fluctuates. This radio station model relies on a powerful software engineering principle known as loose coupling. When a system has loose coupling, it means the software modules act independently. If one piece requires maintenance or breaks down, it has very little impact on the rest of the network. We see this clearly with our toys. The DJ and the listeners do their own jobs, completely separate from one another. They aren't tied together by messy strings or wires. To make this work smoothly, these systems also rely on a second principle called high cohesion. This means elements within a module work together strictly to fulfill a single, well-defined purpose. The DJ only broadcasts, the radio only receives. When developers combine loose coupling with high cohesion, they can build massive, complex digital cities. The individual pieces are incredibly easy to manage, update, and replace without tearing down the entire system. This same logic of sharing updates on a central board or broadcast moves the world's money. Global financial networks use these patterns to broadcast stock prices to investors the moment they change. This architectural diagram shows us how a stock exchange acts as the central hub. It operates as the publisher, pushing out pricing events to multiple connected brokerage firms all at once. We also see this in the Internet of Things, or IoT. Many of our connected gadgets use a system called MQTT. It's essentially a digital language that lets tiny sensors talk to the web without using much power. Imagine a smart thermometer sitting out in a garden. It acts as the publisher, whispering exact real-time temperature data to the internet. This chart shows how sensors use this digital language. On the left, an IoT sensor acts as the publisher, sending data to the central broker. On the right, smart sprinklers act as subscribers, receiving the data so they know exactly when to water. Whether a network is routing billions of dollars in trades or just figuring out when to turn on the garden hose, the pub-sub pattern silently orchestrates the flow of data. By giving digital pieces a shared chalkboard or a common radio frequency, messaging architectures help completely independent pieces of software work in total harmony. Next time, we'll explore how software finds hiding toys using a magic compass as we look at distributed service patterns like the proxy and service locator. Until then, thank you for exploring the miniature city of messaging architectures with us.